Okay, good morning. Looks like we still got a lot of folks just showing up. I know I was a minute late getting that link posted, so I'm gonna give just a few more minutes for folks to arrive. While I do that, I'm gonna take a look at the stats here in the last homework and see whether or not we're going to extend it. I think we probably will extend it just a little bit because we didn't have class last Friday. So you guys haven't gotten all the practice I would like you to get with related rates. It looks like the completion is actually pretty good here. Seems like most folks who opened it got most of it done, but still somewhere around half of us haven't completed it yet, either haven't opened it or haven't quite finished it. So I will go ahead and extend homework 7 to Wednesday. And then today we'll talk a little bit more about related rates. Wednesday, Friday, Wednesday, Friday. Wednesday should be. Fuck it, let's do Friday. Never hurts. Never hurts to get a little bit more time. So I will be opening up homework 8 this week, which is going to cover a few different things. The topics that come up after related rates are linear approximation and then min-max problems, some optimization stuff. So that's where we'll be going next. And that's the material that I'm going to introduce today after we get a little bit more practice with related rates. But since it seems like most people are here now, I'll go ahead and switch to the doc cam. I gotta open the doc cam software, don't I? There we go. So a little update on the exam one. After a careful look at the stats, I have decided to do a score correction thing. So I mentioned that we would potentially be doing something like this for you guys to improve your scores. What I'm going to do is I'm going to allow for one rewrite. If you want to. You can rewrite one free response solution. So today, after I finish with my office hour, I'm going to be breaking apart all of your work. I've got all of your written work for your free response questions here, all stapled up and printed out and marked up nicely with comments. I'll be destapling those and scanning those and submitting them as comments on your exam one scores in Canvas. So I want you to look at the feedback I give you on your test, right? Take a look at the stuff that I'm going to post to Canvas later today. And if you decide you would like to improve your grade on exam one, you can prepare a rewritten, or if you didn't get to a question, you can do one that you haven't done at all, solution to one free response question. And I will score that question completely fresh. So if you got a 0 on it and you didn't get to the problem at all, you now have the opportunity to attack one of those. Or if there was a problem that you worked on, but you weren't happy with the grade you got on that particular problem because something went wrong, you can rewrite that problem and resubmit that solution. And then I will mark that fresh. So this is what felt like the closest thing to a fair way to allow people an opportunity to improve their grades on the test. Like I said, the average was actually right about where I wanted it to be. But the standard distribution, the standard deviation was way too large. So we had a handful of people scoring right around the mean, and we had a handful of people scoring above it, but there was just such a wide curve on the distribution. I'd like to see it clustered a little bit more tightly, and so I thought this might give people an opportunity to bring their stuff up if they wanted to. So I will be uploading written comments. From your free response questions. Today. Review that. Before attempting your rewrite. And then I'll add an assignment in Canvas, a special place for you to upload your rewrites. Make sure you include the problem number on your paper. So include on your rewrite paper first your name, the problem number, and a very careful solution. Explain what went wrong on the original. So like if you just didn't have time to get to the question and your rewrite is a question that you didn't attempt the first time through, then you can just say, you know, I ran out of time. But if the issue was that like you, on that first free response where you're asked to show that that function is or isn't differentiable, I want you to explain how your correct solution differs from your original solution. Like maybe, oh, I didn't realize, but I was showing originally that this function was continuous and I wanted to show that it was differentiable and I just got the definitions crossed up in my head, or something like that, right? So I want a name, the problem number. These things are really important for my organization. It'll help me get through them faster. And then I want you to not just give me a good solution, but explain to me what went wrong in the original solution. Show me that you've really learned something new since then. And that is it. So once, once you have these things, then you'll scan and submit them. Under the new assignment, it's going to be a 0-point assignment in Canvas because I'm going to be going back and adjusting your exam 1 grade based upon it. Once I have all the rewrites in and graded, I will be duplicating your scores and the gradebook will be up to date. Any questions on this? I explained the deal with duplicating the scores last time, but let me really quick show you what I mean by that. So the way the rubric is set up, right now, each exam should be worth 100 points, but the way that the scoring for Canvas quizzes goes, I was unable to make this assignment worth 100 points. So I was, with the true, false, and multiple choice questions marked as they were, as 2 and 3 points respectively, it wouldn't let me like change the weight of each question overall. So your scores for exam 1 right now are in this assignment in the gradebook. So I will be updating this after you give me your rewrites. And then I will just copy paste that score here. And you see each of these is worth 50 points and each test is worth 100 points overall. So that will get you to the 100 points. So only once both of these scores are in will the score in Canvas actually be reflective of what you earned on the exam. So right now the exam is underweighted in the gradebook because you only have out of 50 points. But once we have those rewrites in, I will copy paste those scores here. And then the gradebook will be up to date because you'll have the full 100 points for the test. Nice and clear? Any questions? All right, and everybody's clear what they need to do for the rewrites, yeah? If you're happy with your exam 1 grade, then you don't have to do this at all, right? This is just if you want to improve that grade, if you're not happy with how that turned out, especially if you ran out of time, or especially if you felt like you were unable to study as much as you wanted to, that sort of thing. I want to give you a chance to show me everything you've learned.
So is this still only being able to be pulled up with honor lock? Because
no, this won't be an honor lock thing. So it'll just be an assignment with a little Dropbox where you can upload a thing. So I'm not.
Excuse me, sir.
Yes.
Yeah, but you said that the exam 1 update. So is it like a exercise, homework, or what?
So this will be. This is what I'm doing instead of like curving exam 1, right? So a lot of folks had a difficult time with the test, and I'm thinking of this as something like extra credit or a curve to allow people who are unsatisfied with their test grade to improve their test grade. So this is going to affect the score for exam 1 and nothing else. So this won't be going in as a homework or as a test on its own or anything like that. This is just going to give you the chance to improve the grade on exam 1.
Okay, so when we're gonna submit it?
Yeah, good question. So these are going to be due Friday. So I want to give you time to review the comments, right? After I finish with my office hour today, I'm going to be scanning in all the written comments I have for your tests. I want you to have time to review those and come up with your solution, and then upload that. As long as you get them in by this Friday, I will be happy. And that way I can grade them over the weekend and get your exam 1 scores finalized by Monday.
Okay, thank you.
Of course, of course. Yeah, these are good questions. Any other questions about this stuff? Okay, then last Wednesday, because last Friday was a holiday, we stopped, or we left off talking about related rates. And I'd like to look at 1 or 2 of your homework problems. Some nice alliteration there, related rates redux. So are there any particular problems from the related rates homework, that's homework 7, that you guys would like to take a look at? You can type them in chat there. I did go ahead and extend homework 7 to this Friday for anybody who hasn't been able to get it done yet. Seems like about a quarter of the class got everything done, but about half of the class hasn't quite got it 100% finished yet. Number 17. Oh, would I do extra credit opportunity before exam 2? So Tanzina asks if there's going to be an extra credit opportunity associated with exam 2. Certainly not before exam 2. I don't usually do something like this. So the question rewrites here, this is not something I've ever done. I don't usually offer any sort of curve or anything like that. It's really just not my style. But here I feel compelled to give you that opportunity because it was a new exam format and most people are still getting used to it. And so I think it's very possible that people ran out of time or just weren't used to having to apply their test taking strategies in that situation. It's less likely that I will do something like this for exam 2. Exam 2 will most likely just be scored raw and left as it is. So I would not count on something like this for exam 2. 2, 14, and 17. It was 14. Okay. Okay, in chat, I see questions 2, 14, and 17 requested. Those actually look like a perfect bundle of questions to get started with. So I'll start with number 2 here. So let me get this copied down and then we'll switch back. The earlier questions in this homework set are not related rates problems. They're logarithmic differentiation problems and stuff like that. So here's number 2. They give us this weird function, the natural log of 324 times sine squared x. And then they say find f prime. There's a couple ways we could go about this. So 2 solutions. I could dive in with the chain rule. If I want to differentiate this natural log, that's always going to be 1 over the inside times the derivative of the inside. So I can write it out schematically like that. 1 over the inside times the derivative of the inside. That's the rule for a natural log's derivative. And then if I want to figure this piece out, it's going to require a bit of chain rule because sine squared is a composite function. So I've got 1 over 324 sine squared x times, are you fucking kidding me? My phone just starts blowing up with random spam every day. All right, so I want to differentiate this guy now. So that 324, he's a constant multiple. He'll just come along for the ride. And then I've got a chain rule thing here. So sine squared x, that's going to differentiate to 2 sine x to the 1 times the derivative of sine x, which is cos x. So we can put this together as 324 times 2 sine x cos x over 324 sine squared x. And then finally, I can cancel one of these sines. I can cancel the 324. So I'll have 2 cos x. You gotta be fucking kidding me. Hello? Oh, hi, Karma. Sorry, guys, give me just 1 second. I'm doing well. What can I do for you? Oh, that's okay. I think Ryan might have scheduled that exam mistakenly. So we are not ready for his test 2. They are actually still maybe a week and a half out from that. So if I had to guess, he might have scheduled that with you guys looking at the syllabus. But with the holiday and us having to push exam 1 back, we are still actually a little ways out from exam 2. So I haven't scheduled that for the rest of the class yet. I haven't written it or anything. Yes, yeah, if he's under that impression, then that would be good. No, no exam for that class. Of course. Cool, okay, yeah, sorry for the panic. You too, bye. Sorry, one of my students in one of my other classes got nervous and thought he had a test today when he did not. So, let's come back to where we are.
I have a question, Mr. P.
Yes. Go ahead.
Okay, so you, on the second part, you moved 2 sine x times cosine, correct? Are you using that one from the Pythagorean theorem?
No, this is coming from the chain rule. So the derivative of sine squared x, remember sine squared x is sine x all squared. So if I want to differentiate that, I need the chain rule. First, I differentiate the outer function, which is the squaring function. So I'll have 2 sine x to the 1, and then I multiply by the derivative of the inside, which is cos x.
Perfect. Thank you so much, Mr. P.
Yeah, no problem. Homework 7 is tough. Yeah, I acknowledge that. The related rate stuff, this is one of those sections that a lot of people have a hard time with. You have to be very comfortable with your differentiation rules, especially the chain rule. And the chain rule is kind of challenging. So this is the homework, even though it's not officially the chain rule homework, this is the one that tends to verify that you actually learned the chain rule all the way. And that's not a simple thing. So this piece, the 2 sine x cos x here, is coming from the derivative of sine squared according to this chain rule. And then from here to here, I'm just going to simplify a little bit. So the sine x here is going to cancel into the sine squared downstairs. So he's gone from the top. The 324s are going to cancel. The 2 and the cosine upstairs survive. And downstairs, we just have 1 copy of sine x that survives. So this is it. This is my derivative. Now, this is not how I would recommend calculating this derivative. And I'll show you exactly what I mean. There's a much nicer way to do this. So this is one of 2 solutions that I propose. This is if we jump in right away and differentiate with the chain rule. The other solution, remember what we were talking about, is logarithmic differentiation, where if you want to differentiate some nasty thing, you take the natural log and then expand as much as possible before you start differentiating. So if I wanted to, I could split up my function before I start differentiating. The natural log of 324 times sine squared x, I'll rewrite it down here.
Mr. P,
Mm-hmm.
couldn't you simplify that last, the final answer? To
You could write it as 2 cotangent, yeah. If you
Would
want
we
to.
have to simplify it, or like, could we just leave it as you left it?
I have no problem with you leaving it as cosine x over sine x. That would be okay.
Okay.
So here's the other option. You use the rules for the natural log to split this up before you differentiate. So remember, multiplication inside the log is the same as addition outside the log. And a power inside the log is the same as a multiple outside the log. And this is actually much easier to differentiate. There's no chain rule required, or very little chain rule required, I should say. We don't have a chain rule within a chain rule like we did in the previous solution. You'll see immediately that the 324s go away because this term right here is a constant. So when I differentiate, he will go to 0. And then this will be 1 over sine x times the derivative of sine x. That's the only bit of chain rule we have. So f primed of x is 2 times 1 over sine x times cosine x, which is 2 cos x over sine x like we had before, which you could rewrite as 2 cotangent of x if you wanted to. So I much prefer the second solution. And that's kind of the point of this problem, is to see that this function is easier to differentiate if you expand out the logarithm term first, because it saves you from having to do this chain rule piece with sine squared. It saves you having to futz about with the 324. It's a nicer attack. And the later problems explicitly tell you to differentiate logarithmically, which means take the natural log, expand as much as possible, then differentiate. So if you don't remember logarithmic differentiation. If you've been overwhelmed by the related rate stuff and forgot some of the log differentiation stuff, go look back at last Monday's video, the video from 1 week ago, and at the start of the video from last Wednesday. I think we might have talked a little bit more about that then as well.
So we use that log rule before we do our DDX.
That's the idea. Yeah, so using these log rules to expand as much as possible before taking the derivative gives you easier stuff to differentiate, right? I would rather differentiate the ln of sine x than the ln of 324 sine squared x directly. So this is the only non-constant piece here, and this is much easier to differentiate than the original function. So I would much rather do this first, then differentiate, than try to jump in right away. It saves me from having to do the kind of complex chain rule within a chain rule thing.
And is it 1 over sine x because it's attached to the sine x for the log, or?
Remember the rule for differentiating a log. The ln of some stuff, all primed, it's always 1 over the inside of the log times the derivative of the inside of the log. That's our rule for differentiating ln of some stuff. So the 1 over sine is coming from that.
How did you get from the ln of 324 to 0 below it?
The ln of 324 is a constant.
Oh, I see. It's
That's all. It's just a number.
Derivative below it. I see.
Yep. Yeah. So this piece differentiates to 0 because he is an additive constant. He's a constant term floating around all on his own.
Gotcha. I didn't see the derivative symbol there.
Oh, yeah, no, you're good. There is no derivative symbol here, just here.
Yeah, that's also.
F of x is this, and then therefore f primed is this. Okay, cool, 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 cool. What else are we thinking? Mostly okay?
I have a question.
Yeah, go ahead.
Okay, so where it says so, f prime of x, and you have 0 plus 2 times 1 over sine x, where does times sine x prime come from again?
That's coming from the chain rule. So inside of this natural log is sine x. So I've got 1 over the inside times the inside primed. That's my rule for differentiating logarithms. So here, u is sine x. So the derivative of the natural log of u will be 1 over u times u primed. That's 1 over sine x times sine x primed.
Thank you so much, Mr. P.
Yeah, no problem. Feeling a little better? Any other questions on this fella?
No, but I like that way better, and I now like the DDX better when I write things out.
Cool. Yeah, that's nice. It's fun to see like your preferences in notation change over time as we get a little bit more comfy with these things. So I'm glad to hear that. That's neat. Okay, we also wanted to look at number 14 and number 17, so let me move to number 14 now. So number 14 says y. I'll copy this down and then I'll switch back to the dot cam. Y equals the square root of 2x plus 1. Find dy dt when x equals, oh, let me write it like this actually. I'll copy it as they have it. If dx dt equals 3, find dy dt when x equals 4. That's part A. And part B says if dy dt equals 2, find dx dt when x equals 12. Okay. So this is very much like something you may encounter in a related rates problem. It's understood here that x and y are both implicitly functions of the variable t. So every time I go to differentiate an x or a y, I have to use the chain rule and slap on the time derivative, dy dt or dx dt. If I want to find dy dt, like here in part A, I'm going to apply ddt to both sides. That says take the derivative with respect to the variable t on both sides. So I'm just taking this original equation here that relates x and y, and I'm differentiating on both sides with respect to the variable t, because I'm after dy dt. The left-hand side is exactly dy dt. I'm applying ddt to the variable y, so I get out dy dt. The right-hand side requires the chain rule. So I'll rewrite this as ddt of 2x plus 1 to the 1/2 power. And then I'm going to give myself a little partition here so I can continue on the other side. My left-hand side is dy dt, and it's going to stay that. But my right-hand side now, I have to apply a couple rounds of chain rule. So first, I differentiate the outer function, which is that 1/2 power. So I'm going to bring the 1/2 down and reduce the 1/2 power by 1, and then multiply by the derivative of the inside. So I'll have 1/2 2x plus 1 to the negative 1/2 times ddt of 2x plus 1. And then I continue. My left-hand side is still dy dt. I've got my 1/2 2x plus 1 to the negative 1/2. And then ddt of 2x plus 1. That's 2 dx dt. So just like ddt applied to y is dy dt, ddt applied to x is dx dt. The 2 is a multiplicative constant, so he comes along for the ride, and the 1 differentiates to 0. He's an additive constant. So this is my differential relationship. And then they told me that dx dt is 3 and x is 4. So finally, I will plug those things in. So dy dt is 1/2. 2 times 4 plus 1 is 9 times 2 dx dt I was told is 3. So 9 to the negative 1/2, that's 1/3. 1/3 times 1/2 is 1/6. 1/6 times 6 is 1. So this is 1/2 times 1/3 times 2 times 3, which is 1. So I think the hard part here is getting to this step. So take a look at the work we did. Here I just applied ddt to both sides. Here I just rewrote the square root as the 1/2 power. And I rewrote the left-hand side as dy dt because ddt of y is dy dt. From then on, the left-hand side doesn't change. Here, I wrote out what the chain rule tells me to do. I differentiated my outer function. I brought down this 1/2 power and reduced that 1/2 power by 1. That gives me the negative 1/2, leaving the inside alone. And then I multiply it by the derivative of the inside. The derivative here is with respect to time. So it's d dt of 2x plus 1. Normally, I would write 2x plus 1 primed here. But remember, the prime notation is a little bit ambiguous. It doesn't tell you whether you're differentiating with respect to x or y or t. So instead of using the prime notation, I just use the Leibniz notation d dt for the derivative of the inside. Then this derivative, d dt of 2x plus 1, is just 2 times dx dt. So that gets me to here. And then from here, I just plug in. They told me to plug in x equals 4. 2 times 4 plus 1 is 9. So I get 9 to the negative 1/2. That's coming from this piece. And they also told me to plug in 3 for dx dt. So dx dt is 3. 2 times dx dt is 2 times 3. So this is 1/2 times 9 to the negative 1/2 is 1/3. So I get 1/2 times 1/3 times 2 times 3, which is 1/6 times 6, which is 1. For part B, I don't need to start fresh. For part B, I can take this relation right here and use it to finish what I'm trying to do. So in part A, we learned that dy dt is equal to 1/2 times 2x plus 1 to the negative 1/2 times 2 dx dt. So if dy dt equals 2 and x equals 12, we have dy dt is 2, so I have 2 equals 1/2 times 2 times 12 plus 1 is 25. And I want to solve for dx dt. This 1/2 and this 2 cancel. 25 to the negative 1/2 is 1/5. So I get this. And then multiplying both sides by 5, I get that 10 is equal to dx dt. So I'm really glad we looked at this problem. This is exactly the sort of stuff that we need to be getting comfy with in order to be rock stars at related rates. So I'd really like to hear whatever you guys have to ask about these steps. And then after we've talked about that, we can talk about anything else in the problem. So questions about this stuff, particularly anything that leads us to here.
So they were using the chain rule, correct?
Yes. Yeah, we're using the chain rule to differentiate this piece. So the 1/2 comes down and I reduce the power by 1. 1/2 minus 1 is negative 1/2. And then I have to multiply by the derivative of the inside, the derivative of my 2x plus 1. The derivative ddt of 2x plus 1 is 2 times dx dt. So the plus 1 differentiates to 0. The 2 stays attached to the x piece, and the x piece turns into dx dt.
Got it. Thank you.
Other questions about how we get to here?
No, but you say we have 2 equals. Where did that come from?
Down here?
Yeah,
So I'm taking this expression
right.
and I'm plugging in these values.
Oh, silly. Okay, thank you. dy dt is 2. I see.
Yep. Yeah, they said if dy dt is 2, find dx dt when x equals 12. So they're telling me plug in 12 for x and 2 for dy dt, then solve for dx dt.
Too easy. Thank you.
That's not too bad, no. What else are we wondering? Any other questions on this one? Okay, if you haven't gotten to this one in the homework yet, again, I've got the homework 7 open until Friday, so you can spend some more time on it. Go back and do it fresh, right? Have these notes somewhere nearby so you can refer to them if you get stuck. But stab away at this for, I don't know, 15 minutes or so, 20 minutes without looking at the notes, and see if you can arrive at this place. Because that is the main skill that we need to be practicing right now. The last one that we wanted to look at from the homework before talking about the new stuff is number 17. So let's take a look at him. This is, yeah. So homework 7, number 17. So basically what you have here is this big cone. And we're told that the kind of frame for this cone is an equilateral triangle. Is it equilateral? Or just isosceles? So conveyor belt coming off at this, and its coarseness is such that it finds shape of a cone's diameter. Oh, diameter and height are always equal. Okay, how fast the height of the pile increasing when the pile is 8 feet high? So you have a cone whose volume is growing at 20 cubic feet per minute. The height and diameter are always equal. Find how the height is changing when the cone is 8 feet high. Okay, so here's the important stuff. I've condensed the phrasing a little bit. So we have a cone whose volume is growing at 20 feet cubed per minute. The height and diameter are always equal. Find how the height is changing at the moment when the cone is 8 feet tall. So I'll draw the picture here. Here's the height. Here's the radius. The height I'll label as H. The radius I'll label as R. And because the height is always equal to the diameter, that's the same as saying H is always equal to 2R. So this would be my first step, right? Just drawing this picture, picking some variables, labeling my picture, and then seeing how the words give me a relationship between H and R. Then we have to ask what else is going on here? Well, the volume of the cone is changing. So we're also going to need an expression for the volume of a cone. Does anybody know what that is?
I think 1/3 HR squared.
Yeah, very close. 1/3 HR squared times pi.
Pi. Okay.
Yep, so this is the volume relation. This ties together the volume, the radius, and the height. What I'm after is the rate of change of the height, which is dH dt. So this is always how I set these up, right? First, draw the picture. Then, figure out any obvious equations that come from the statement of the problem, like the height is always equal to the diameter. That means h is always 2r. And the volume of a cone is clearly important here because we're told that the volume is growing at da 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 da, right? The volume is one of the important things discussed here. So write down any obvious algebra statements that come from the problem, draw your picture, and then identify what it is you're after. I want dH dt when h equals 8. So do you see how this is kind of similar to the last problem? I'm asking for the value of some derivative at some particular moment. And here, instead of being given one expression like y equals the square root of 2x plus 1, I have these two expressions. This is going to be the one that I differentiate because the volume's rate of change is the only rate of change that I have to work with. I'm told that the volume is growing at 20 cubic feet per minute. So I'm going to differentiate through here with respect to time. But before I do that, I'm going to use this relationship to get this guy down to a single variable, to get rid of this r squared. So I'm going to come down here to do the actual calculus work. Since h equals 2r, we know h over 2 is equal to r. So v, my volume, is really 1/3 pi times h over 2 squared times h. In other words, v is, let's clean this up a little bit. I'll have my 1/3 pi, and then h over 2 squared is h squared over 4. So that's going to be pi over 12 times h squared times h is h cubed. Everybody see how this simplifies to this? H over 2 squared, that's h squared over 4. So 1/3 times pi times 1/4, that's the pi over 12. I lumped all the constants together. And then h squared times h is h cubed. Hence, I applied ddt to both sides. The pi over 12 is a constant. My left-hand side is dv dt. And over here, I'll have pi over 12 popping out because he's a multiplicative constant times the time derivative ddt of h cubed. Now I take this derivative, and again, it's a chain rule thing, right? I'm differentiating with respect to t. So h here is understood to be a function of t. So I'll have 3h squared, that's my derivative of the outer, times dh dt. That's the derivative of my inner. And now the 3 and the pi over 12, these guys will talk to each other a little bit. This will become pi over 4. So my final relationship here is dv dt equals pi over 4 h squared dh dt. And once I arrive at this point, I want to stop and ask, okay, what am I hoping to do? I want dh dt at the moment when h is equal to 8. So I'm going to come down here and I'm going to plug in 8 for h and try to solve for dh dt. The thing I don't have right away is dv dt. Can anybody tell me what dv dt is?
Is it what we were given in the beginning? The
Yeah.
20 cubic feet?
Right, yeah, the volume is growing at 20 cubic feet per minute. So the volume is increasing, so dv dt is positive, and it's increasing at a rate of 20 cubic feet per minute. So dv dt is 20. Very good. All right. So I'm going to plug dv dt equals 20 and h equals 8. That'll give me 20 equals pi over 4 times 8 squared dh dt. And I'll zoom back in down here. So it's this piece that tells me dv dt is 20. So from here, it's straightforward, right? I just want to solve for dh dt. So this is the same as 20 equals pi over 4 times 64 dh dt. 64 divided by 4 is 16, so 20 equals 16 pi dh dt. So 20 over 16 pi equals dh dt. And there's a factor of 4 here that you could cancel, so 5 over 4 pi equals dh dt. So in other words, at the moment when the height of the cone is 8 feet, the height is changing at a rate of 5 over 4 pi feet per minute. In other words, the cone is growing at 5 over 4 pi feet per minute. So this is definitely a classic related rates problem. Take a second and make sure your notes are complete. Make sure you have all the stuff that you need. Our starting observations were these. Since the height is equal to the diameter, h is equal to 2r. Remember, diameter is always twice the radius. So 2r is the diameter. So h equals 2r. And the volume of a cone we know is 1/3 pi r squared times h. The way I remember this is that pi r squared, that's the area of a circle. That's the circle at the base. And so you multiply by 1/3 h to get the volume of the cone. Then we identified what it was we wanted. I'm after dh dt. So I need to differentiate something with respect to time, and that something had better contain some h's, and it had also better be something I can plug into with the information I have. So differentiating this volume relationship is what makes sense. In order to make this easier to differentiate, I'm going to plug in what this tells me, right? I'll get rid of the r's. That way I'll just have v's and h's because I know dv dt and I want dh dt. So I want to get rid of the r's. The way I get rid of the r is by using this relationship. Since h is always equal to 2r, we know h over 2 is always equal to r. Just divide both sides by 2. That means anywhere there is an r in this equation, I can replace it by h over 2, and that gives me this. Then I simplify this as much as possible algebraically before taking any derivatives. Simplifying this gives me this. Once I have this guy, then I go ahead and take my derivative. I applied ddt to both sides. ddt applied to v is just dv dt. ddt applied to the right-hand side, the pi over 12 pops out, and I just get ddt of h cubed. That is an implicit differentiation thing. That is a chain rule thing. So I differentiate the outer function, that's the cubic power here. So I bring that power down, reduce the power by 1, and then I multiply by the derivative of the inside. I multiply by dh dt. That gives me this final relationship between dv dt and dh dt. I know dv dt. dv dt is 20 because the volume of the cone is growing at 20 cubic feet per minute. And I was asked what's happening at the moment when h is equal to 8. So I plug those two things in to this relationship. When I do that, I get this. dv dt is 20, h squared is 8 squared. And then I just simplify and solve for dh dt. So these problems, they're not horrendous. And once you get enough practice with them, they're actually very intuitive. These are exactly the sort of problems that you want to get good at if you intend on taking Physics 1, or really anything that involves applications of calculus. So economics, higher level statistics, all require this sort of manipulation. So let's take questions on this. What are we wondering? What feels weird?
How did we go from 3h squared to the h squared again down there? Did you divide underneath the fraction there, or?
So the pi over 12 times 3 over 1.
Oh, duh. I see now. Thank you.
Yeah, that's all. Yeah. So the 12 is 3 times 4. I cancel the 3's. That's all. What else are we thinking? Does everybody see where this guy came from? So I have this constraint that h is always 2r, and that allows me to simplify my volume equation down to this, which is easier to differentiate. So any questions about where this comes from or any of this work? Mostly okay? Let's see if there's another problem here we could take a look at. Well, there's really not a whole lot here for you guys to practice on besides these. I would like you, yeah, we've already done this one. I don't want to spoil the rest of these for you. So like I said, this homework is going to stay open until Friday. So please continue working on it. If it feels really intimidating to you, I would recommend going back and watching Monday and Wednesday's videos, maybe even rewatching this one. You can watch them at like 1.5 speed on YouTube so that they go faster through the boring parts, and then you can slow them down when they get to the stuff that is difficult. But make sure you're taking notes as you go, and continue working through the example problems. There's also lots of good example problems in the textbook. If you, Sumatra, please. So you can work through any one of these problems in the textbook also, right? If you work through these with pencil and paper, rather than just reading them, I think you'll find that that will be really helpful when you get to the homework also. So they're doing all the same sort of shit that we're doing here. But we need to start talking about this stuff, linear approximation. Like related rates, this tends to be one of those things that folks have a bit of a hard time with. So I'm going to introduce it gently as I can. But there will be a new homework this week, and the homework will have some linear approximation and some min-max problems on it. So section 3.10 on linear approximation. Do you ever wonder how we know pi is like 3.14? Or how we know the square root of 2 is like 1.4?
Yes.
Like, it's weird. How do we get these approximations for irrational numbers?
Using linear approximation.
Yeah, that's one of the ways to do it. Yep. So the basic idea is this. Near the point a comma f of a on the graph of the function f of x, as long as you stay close to that point, the tangent line is a good approximation for f of x itself. That's the big idea. In fact, in a much more grown-up calculus class, in like a second or third year graduate level differential geometry class, we define the derivative to be the best linear approximation to that function at that point. So if I have some function here, f of x, and I take some point a comma f of a, so here's a, and here's the point a comma f of a, and I look at the tangent line there. Notice that if I stay reasonably close to a, so I take some x value maybe right here, there's not a big gap. The gap between f of x, the curve, and the tangent line is small, right? There's just a tiny, tiny little gap in there. So if I wanted to know the y value on the curve, I could approximate it using the y value on the tangent line. i.e., here's, where do I say this? Right, the y value on the curve here is very, very close to the y value on the tangent line there. The y value on the curve is f of x because it's the y value associated with the input x. The y value on the tangent line remember the tangent line can always be written as y minus f of a equals f primed of a times x minus a. So you can solve this for y. Y equals f of a plus f primed of a times x minus a. So the y value here should be very, very close to the y value there. In other words, f of x is approximately f of a plus f primed of a times x minus a. And this is what's called the linearization of f at a, or the linear approximation for f of x near the point a comma f of a. And the whole idea there is that if you stay close to the point of tangency, as long as you don't wander too far away from this point, this line will stay pretty close to the curve. Of course, the further you get away from the point of tangency, the less good that approximation becomes, the bigger the gap becomes. But as long as you stay reasonably close, the gap here will be very, very small. This is going to do a number of things. One of them is that it's going to allow you to approximate shit like the square root of 2.
That says gap between f of x, parentheses.
Oh, curve, sorry. So yeah, the gap between f of x, which is the curve, and the tangent line is small. So the gap between the curve and the line is small. So this object here is called the linearization of f of x at the point a comma f of a. And all it says is that if you want to know f of some number, you can plug that number into the tangent line. And as long as the number you're plugging in is close to the point of tangency, you'll get a good approximation. Linearization just means we're taking f and we're doing our best to turn it into a linear function. Even though f is not linear, there is a linear function that does a good job of approximating f, at least near a point. And the linear function that does the best job is the tangent line. Okay, so take a second, make sure you have all this in your notes. And then we'll see how we make use of it. So I don't want this meeting control stuff to be in the way. I'll put it there for now. If you take Calc 2 with me next semester, I'll talk with you about how to extend this, how to make this better. And that leads to what's called a Taylor series. But for now, we're just going to look at the linearization. Anything here that we're having a hard time reading or we'd like to talk about a little bit more before I show you an example?
I think we're good, or I am.
Okay. So use linear approximation to estimate the value of, I guess I should grab an example from your textbook so I don't end up wandering through a more difficult problem than we want to. I usually like to do the square root of 2, but yeah, that's a little bit tricky. So let's do it like this. Linearization of this, I equals 1, we need to approximate the square root of 4.05. Okay. So, use this to with the function f of x equals the square root of 4 plus x at, what is it? Oh no, sorry, square root of 3 plus x. You want us to do it like that, really? At a equals 1. Okay. All right, we can do it like this. So I want to give you some intuition for what we're doing here before we jump into the calculation. So let me pull up Desmos. Here's my function, 3 plus x. I'll write it as f of x equals 3 plus x. And what I want is to approximate the square root of 4.05. So to get the square root of 4.05 out of this, I would be plugging in 1.05, right? So if I find the linearization for f of x at 1, then I can plug 1.05 into that instead. So in other words, what I'm going to do here I would have to crunch that all out separately. So yeah, I'll just come back here and show you. So observe that the square root of 4.05 is equal to f of 1.05, right? Because if you plug in 1.05 for x here, 3 plus 1.05 is 4.05. So we want to approximate f of 1.05. According to the linearization, f of 1.05 should be approximately equal to f of a plus f primed of a times x minus a if a is close to 1.05. Right? This is my linearization formula. And it says f of x is approximately equal to f of a plus f primed of a times x minus a. Oh, I'm sorry, this should be a 1.05 minus a. As long as a and x are close. So I'm going to build the linearization. In other words, I'm going to find the tangent line at a equals 1. So f of a is f of 1 is the square root of 3 plus 1 is the square root of 4, which is 2. F primed of x is the derivative of square root 3 plus x, which is the derivative of 3 plus x to the 1/2, which is 1/2 times 3 plus x to the negative 1/2 times, by the chain rule, I need the derivative of the inside, but the derivative of the inside is just 1. So this is 1 over 2 square roots of 3 plus x. So f primed of a is f primed of 1 is 1 over 2 times the square root of 3 plus 1, which is 1/4. Right? 1 over 2 times the square root of 4 is 1 over 2 times 2 is 1/4. Therefore, the linearization of f of x at a equals 1 is f of x is approximately equal to f of a, which is 2, plus f primed of a, which is 1/4 times x minus 1. So let me just come back here to my Desmos graph. All right, everybody sees what I'm doing here. I'm essentially finding the tangent line. So I find my point. My point is 1, 2. I take the derivative and I plug in 1 for x to give me my slope, which is 1/4. And then here, this is just the tangent line solved for y. So I'm going to add my linearization. I'll call it g of x equals 2 plus 1/4 times x minus 1. So notice that as long as I stay close to this point, the black and the red are very, very close to each other. What I'm looking for, I want to approximate f of 1.05. That's like the y value on the red here. So this is the point, I want to approximate. And the point I'm going to use, this is the point used for approximating. So you see the red and the blue points are almost completely indistinguishable. Their y values are almost identical. The red point is on the red graph, and I'll change the blue to black. The black point is on the tangent line. The difference being, it's very, very easy to plug into the black function because it's a linear function, but it's quite hard to plug 1.05 into the red function because it's complicated. It's the square root. So the square root of 4.05 is exactly equal to f of 1.05. And f of 1.05 is approximately equal to what you get when you plug 1.05 in here. 2 plus 1/4 times 1.05 minus 1. Which is 2 plus 1/4 times 0.05.
Can you zoom in
And,
the bottom half a little bit, please?
yeah, sure.
Thanks.
So we build the linearization at a equals 1. To do that, I need to come up with my point and my slope. So my slope is 1/4 and my point is 1, 2. So my linearization, I just plug into my formula, is this. And then I observe that f of 1.05 is exactly what I want, the square root of 4.05. And that's approximately equal to what I get when I plug 1.05 into this, the linearization. Now 1/4 times 0.05, my arithmetic is bad. We could write it as a fraction, but 0.05 divided by 4 as a decimal is 0.0125. This is...
Actually, Mr. Let me take the picture of the whole page.
Sure. So there's the problem complete. Now, Hutanji wants to take a picture of the whole page. Angelica wanted me zoomed in
Yeah.
from here, so give me just 1 second.
Okay.
I will zoom out here so we can get the whole page in. I'll zoom in just a little bit to try and improve focus. All right, I think this is as good as we can do. I can move this over to get that meeting bar out of the way. All right. So there's everything all at once.
Okay, thank you, sir.
We know that the square root of 4.05 should be just a little bit bigger than 2 because the square root of 4 is 2 and the square root is an increasing function. So it's 2 plus some small number, but I'm not sure what that small number should be. In order to figure it out, I use the linearization formula, which means I need to build this formula. To do that, I come up with my point and my slope, just like because it's a tangent line, that's all it is, it's the tangent line. And then I write down the formula. F of x is equal to f of a plus f prime of a times x minus a. A is 1, so f of a is 2. F prime of a is 1/4. X minus a is x minus 1. And then I'm guaranteed that the linearization, this thing, is close to f of x. So if I want to know what is f of 1.05, because that is what I want to know, the square root of 4.05, which is f of 1.05, I come back down here and I plug in 1.05 for x. F of 1.05, which on the one hand I know is the thing I want, should be approximately equal to this shit with 1.05 plugged in for x. And then I just simplify. So the square root of 4.05 is a little bit bigger than 2, and it's bigger by 1/4 times 0.05, or 0.0125. So the square root of 4.05 is about 2.0125. Do we see it? I'll give a second longer if you're writing or if you want to ask questions. Exam 2, so there's a question in chat there about when exam 2 is going to take place. We are getting close, but I don't think we're quite that close yet. Let me see, oh, you guys are over here. There's our syllabus. Here it is. So after we talk about linear approximation, we have to talk about min-max problems, and then we have a whole week's worth of material and then exam 2. So not next week, but the week after. Exam 2 will be the week after next.
The week of the 20th.
That sounds right. Yeah, yep, the week of the 20th.
After final exams. Thank you.
Oh, is that the summer A final exams right around then?
D, I think it
Summer
is.
D?
Yeah,
I see.
14th. So yay, thank you.
Oh, I'm sorry. Yeah, it is the case that these summer classes are a little bit rushed.
No, that's good. I'm glad it's not the same week.
That's true. Yeah, it could be worse. Could be worse. Okay. So let's look at another example problem or two here. Of physics. Oh, it's the small angle approximation. We can do this. Do they do this? Oh, well, that's not super exciting here, is it? What would be fun though? No, they're talking in terms of differentials. We don't want to fuck with that. So we're not going to talk about these things in terms of differentials. I don't find that to be especially helpful. It's the same stuff, just in different language. So let's play around with one more. We just did a square root, so maybe something like linearization of that at equals 4. That's a little bit too similar to what we just did. 2 to the x around 0. That's not really going to help. Let's do number 5 here. You guys see number 5? Find the linear approximation to this function at 0 and use it to approximate these square roots. Illustrate by graphing f and the tangent line. Okay. Or maybe we should do this harder one. Yeah, the one we just did was a square root. We'll do both. Okay. So. So we're going to find the linearization to the function f of x equals the square root of 1 minus x. And then we're going to use it to approximate those two. Oh, shit, no, but we're out of time. Okay, yeah, so this is where we will pick it up on Wednesday. So I won't be doing this example right now, but I'll leave this page up here so we can start on this on Wednesday. It'll be the same thing that we just did. We're going to calculate the point. So my point, f of a would be f of 0, which is the square root of 1, which is 1. So my point is 1 comma 1. And f primed of a, I'll find this by calculating f primed of x, which will be 1/2 1 minus x to the negative 1/2 times -1 or -1 over 2 square roots of 1 minus x. So f primed of a is f primed of 0 is -1/2. And then we'll build our linearization. But I'll leave this here and we can come back to this on Wednesday. Reminder, there is that option to improve your grade on exam 1. So watch later today for comments in Canvas on your exam 1 grade, because that will be the feedback that I'm uploading. And then if you would like to rewrite one of those problems, you may do that. Just make sure you have your solution submitted by Friday, and there will be a separate Canvas assignment for that. So I'm gonna go.
Okay, sir. So about the true or false, so what we're gonna do, we have to write down or what, so. You know some question concern about true or false.
Yeah, the true or false you cannot rewrite. So the rewrites, you can pick one free response question and rewrite your solution. So if there was a free response question you didn't get to, or a free response question that you're unhappy with your grade on, you can rewrite that question and that question only. So none of the true, false, or multiple choice are available for rewrites, just one free response question.
Sorry, I don't understand.
I'll post a Canvas announcement a little bit later today with some really detailed instructions. Unfortunately, I don't have time to go over it again right now. But
Okay.
either rewatch this video after it's up on YouTube at the beginning when we talked about it, or read the announcement I'll post a little bit later today. But right now I got to shuffle off because I have another class. But yeah, you'll be able to read
Okay.
solutions to one free response question. That's all.
All right.
I will see you guys either in office hours or on Wednesday. Remember to keep working on homework 7 and watch for homework 8 to drop, and work on those rewrites once you have your feedback. All right, I'll see y'all later.